If we search for this word probability in any dictionary, usually we find that it does mean chance or possibility or likelihood of occurrence of an event. But when we think about probability in mathematical point of view, we look for a number in closed interval 0 to 1. That means a quantity which can be any value between 0 and 1, including 0 and 1. But why do we need a quantity as measure of probability? And how can we measure probability? At first, let's try to find answer to this question. A simple reason to quantify something is it helps us to control that thing. A very elementary example I can take here. Suppose here is a jar, cubed shaped from inside. It can hold 4 liters of water. Here is an outlet tap attached. If I open this tap, water will flow out of the jar. Now my task is, after I open this tap and the water starts flowing out, I have to close this tap just when the water in this jar reaches the halfway level. Let's open this tap, close it, some water flowed out, but it has not reached the halfway level. Let's open it once again. It reached near the halfway level, but not exactly the halfway level. We cannot close the tap at right moment to let the water reach halfway level here. But if I mark the level of water this way and open this tap to let the water flow out, little more, close it, I'm able to close the tap at more accurate moment just because I quantified the level of water here, which helped me to understand the level of the remaining water inside better. When it reached the halfway, I closed the tap. Here I quantified level of water, which is a matter with physical properties. We can see it, we can touch it. Now, is it possible to quantify a concept like chance or probability also, so that we can do better decision making from our predictions based on measures of probability? How? This same question was first attempted by Italian polymath Girolamo Cardano to find answer in the year 1550, and later Blaise Pascal, Pierre de Fermat, these two French mathematicians, while trying to calculate the number of turns required to ensure obtaining a 6 in the roll of 2 dice, which was related to a gambling problem posed by the French writer Chevalier de Magie in the year 1654. His gambling habit perhaps was the main reason of starting of the study of probability through these two mathematicians. Consequently, it was the beginning of probability theory. But there was no particular mathematical definition of probability yet. Before we try to understand probability mathematically, few basic terminologies and concepts we need to know. In our everyday life, so many things happen. Outcome of some of the things are deterministic or certain. As example, a new day always brings a sunrise and starts with daylight, a deterministic or certain event. But a new day not always starts with sunny morning. It can be rainy also. That means weather has no deterministic event. It has several possible outcomes. It can be sunny, rainy, or cloudy. Our study of probability begins when outcome of an experiment is not deterministic. Rather, it is probabilistic as it has several possible outcomes. As example, here watching a new day is an experiment with deterministic outcome, daylight. Watching a new day weather is another experiment with these probabilistic outcomes. In probability theory, this kind of experiment we refer it to as random experiment. Now, what is called a random experiment? Remember, every time we perform an experiment, it is called a trial of the experiment. And if in each of the trials of the experiment performed in absolutely similar conditions one after another, the outcome result is not unique. Rather, the outcomes are random. That means a particular outcome occurs from many of the possible outcomes. Such an experiment is called random experiment. The simplest example of a random experiment will be tossing a coin. In a trial of tossing a coin, we can get head or a tail. These are two possible outcomes, out of which only one outcome we can get as the result in a trial of tossing the coin just once. Another example of random experiment is throwing a die. In a trial of throwing a die, we can get one out of these 6 possible sides facing upward. Here, collection of all individual possible outcomes, that means the set of all possible outcomes in a trial of a random experiment, we call it as sample space. In a trial of this random experiment tossing a coin, these are 2 possible outcomes, head and tail. Hence, the sample space for this random experiment can be this set containing H for head and T for tail. Each of these distinct outcomes in a sample space we call as sample points. These sample points in a sample space we call equally likely if no outcome is more likely to occur than another. That means here we say head and tail are equally likely to occur when the coin is fair. There is no chance that any sample point out of head and tail can be preferred. Similarly, in a trial of throwing a fair die, these are 6 equally likely face values 1 through 6, which will be in sample space of this random experiment. In a random experiment, as example here in a trial of tossing a coin, we may think apart from head and tail, many other outcomes also can occur. Just imagine while tossing, if the coin does not come back, or if the coin lands on its edge, stands vertically without showing any face up like this. These outcomes should we consider as sample points anyhow? Not actually, because we must perform a random experiment with proper equipments in a standard environment where it can produce a definite observable outcome by eliminating any vagueness or surprise. For this same reason, when we throw a die, we cannot consider the situation of landing the die on its corner as a sample point. These outcomes for tossing a coin and here these outcomes for throwing a die altogether build up the respective sample spaces by staying as distinct sample points in the sample spaces. That's why we call these possible outcomes as exhaustive outcomes or cases. If we eliminate any case from here, sample space will not be formed. All these outcomes are distinct here. As example in throwing a die, if the die lands with the value 2 facing up like this, we take 2 as the outcome only. We cannot say 2 and 4 or 2 and 3 both are outcomes. That means outcomes are not overlapped on each other. That's why we say these outcomes are pairwise mutually exclusive. So far we see these sample points in sample space are countable here because these are just 2 examples of discrete sample space. Later we will see continuous sample space with uncountable sample points also. Now any subset from a sample space we can get is called an event. There are so many types of events exist, we will know gradually. If an event is just a singleton set, we call it a simple event. As example, a subset from this sample space holding H for head only will be a simple event. Here a subset from this sample space containing 6 only will be another simple event. If an event can be expressed as union of 2 or more simple events, it is called a composite event. As example from here, if we take an event containing 3 and 5, it is a composite event. Similarly 2, 4, 5, it is another composite event. 1, 3, 6. It is another composite event. If two events don't have any sample point in common, those events will be called mutually exclusive. As example here, D3 and D4 are mutually exclusive because the intersection of these two sets is a null set. It contains no sample point. But D2 and D3, these are not mutually exclusive because intersection of these two events is not a null set. If union of two or more events can form the whole sample space back, we can call those events as exhaustive events of the random experiment. As example here, if we take union of D3 and D4, notice that we get back the whole sample space of the random experiment throwing a die. Hence, we can say D3 and D4 are two exhaustive events of throwing a die. But if we take union of D2 and D3, it does not give the whole sample space. Hence, D2 and D3 are not exhaustive events of throwing a die. Again, if we take union of all these three events, then also we can get the whole sample space back. So we can say D2, D3 and D4, these three are also exhaustive events of the random experiment throwing a die. We have enough terminologies and basic information to interpret probability mathematically. Let's see how to define probability now. If a trial of a random experiment results in any of the exhaustive, mutually exclusive and equally likely outcomes, or we say cases, in sample space S consisting of n of S number of sample points, then the probability of occurrence of an event A containing n of A number of sample points in it is defined by this ratio: count of sample points in A to count of sample points in S. Here P of A represents the probability of the event A. This definition is referred to as classical definition of probability, and it was identified with the work of two mathematicians, Swiss mathematician Jacob Bernoulli and French mathematician Pierre-Simon Laplace. Now we will use this definition of probability for calculating probability of an event in any random experiment. See you in the next video.